Right. In the 19th century, solar cells are made from semiconductor materials. One type of solar has two layers of semiconducting material, layer 1 and layer 2. Photons of light incident on the solar cell as shown. The minimum energy to release an electron from a semiconductor layer is a work function. Right here we have a diagram. The work function of layer 1 is 1.86 electron. Calculate the minimum frequency of light needed to release an electron from layer 1. Right here, first thing what you have, I hope you remember that the minimum uh, frequency of light can be obtained by using HF equals that, because that would be equal to at least the work function, or the work function, the energy of the photon, right? Okay, then here they have given it in what, electron volts. So if you want to get the frequency in hertz, what you have to do, you have to convert this energy into joules. So it is 1.86 times electron volts times, right, 1.6 times 10 to the power minus 19 joules. So if you convert this one, what you will get for your energy is 2.98, 2.98, right, 2.98 times 10 to the power minus 19 joules, right? So that is equal to HF. The frequency, it is equal to, here it is 2.98 times 10 to the power minus 19 joules over the Planck's constant. It is 6.63 times 10 to the power minus 34 joule second. So if you calculate this one, you will get 4.49 times 10 to the power 14 hertz. That's your answer. So if you make it into two significant figures, it is 4.5 times 10 to the power 14. Right. In the next one here, light from the sun is incident on the solar cell. The intensity of the incident light is constant. Layer 1 has a greater work function than layer 2, right? Keep in that your mind what the work function of layer 1 is greater than what work function of layer 2. Right? Photons not absorbed by layer 1 are transmitted to layer 2. Layer 1 is removed from the solar cell so that all photons now reach layer 2. Explain how removing layer 1 affects the rate at which electrons are released in the solar cell. You should assume that each layer absorbs all photons with a frequency greater than the minimum frequency for the layer, that layer. Right. In this case, right, we need some assumption. You already know this thing, right? This thing is one photon reacting with one electron, right? It will release one electron, interacts with one electron. And if you consider the rate of, if this is our solar cell, whatever it is, right? Here, the number of photons, right, emitting our solar cell. Here we have the layer 1, and here we have the layer 2. Number of photons coming to the solar cell is constant, right? You don't need to worry about that one. So if you remove this one, right, the layer 1, and here they have mentioned layer 1's work function is greater than layer 2, right? So if you remove the layer 1, then they all will meet layer 2, and you don't need to worry about that one because the work function of the layer 2 is smaller than the work function of the layer 1. So they will emit electrons like exactly as the previous stage, right? So how can we write this with step by step according to 5 marks, right? I'll write this one. First thing you have to mention what the number of photons reaching or arriving each second on the cell is same. Arriving each second on the cell, on the cell is same, right? Layer 1 absorbs photons. layer 1 absorbs photons with a greater frequency, right? And photons reaching layer 2, right? Photons reaching reaching layer 2, right, have an energy greater than the work function of layer 2, right? Uh, an energy greater than the work function of layer 2. Layer 2, right? Okay. Then one photon interacts with one electron. Then you can write our conclusion. So what? The rate, the rate at which electrons are released, released remains the same. So if you write these 5 points, you will get the whole 5 marks. 1 mark for this one. And layer 1 absorb photons with a greater frequency, right? Frequency. Uh, then photons reaching layer 2 have an energy greater than the wave function of layer 2, right? One photon interacts with one electron. So the rate at which electrons are released remains the same, right? Uh, Here in the part C, right here, the student connected two solar cells in series with 4 ohm resistor as shown. The student adjusted the light conditions so that each solar cell had an EMF of 5 volts and an internal resistance of 0.80 ohms. The power dissipated in resistor was 30 volts. The student suggested that connecting the cells in parallel would cause the power dissipated in the resistor to be less than half this value. Deduce whether the student's suggestion is correct. Right. Let's do it. Right. So first thing what you have to do here is, right, if you are connecting also, right, if you are connecting these two solar cells, right, in parallel to each others, then what will happen? Right. You have to calculate the equivalent resistance in this case. So R E is equal to 1 over R1 plus 1 over R2. 1 over R1 is 0.8 ohms. They have given it plus 0.8 ohms. Right. Okay. Then if you calculate this one, you will get the RT 0.40 ohms. Then, right, you are connecting this with a resistor. So now I'm going to draw another diagram for to uh, how can I tell you to show this much more in a much more simple way, right? So this is our resultant solar cell, what I call. Then that's the internal resistance of this one, that the resultant internal resistance, and then we have the resistor over here, right? So here 5 volts over here, and here also 5 volts. So you don't need to worry. Here will be 5 volts. And what about the internal resistance? It is, we already calculated, it is 0.40 ohms. And here we have 4 ohms. Now, right, by using what voltage divider method, we need to find the voltage across the resistor. I will call it VR. VR is equal 5 volts. time we have to use what voltage divider method. So it is 4 ohms, right? 4.0 ohms over, right, here, 4 ohms. So if you simplify this one, what you will get here is equal to 4.55 volts. So by using the same principles, right, we can calculate the current, right? Current is equal to 1 V over R. So here we have 5 over here, and the R will be what the total resistance. It is 4 ohms plus 0.4. So I'm writing it 4.0 ohms plus 0.4 ohms. So if you simplify this one, what you will get here is 1.14 amperes. Now you know the V and you know the current, then you can calculate what power dissipate. So it is equal to V times I. So V is 4.55 volts, and current, it is equal to 1.14 times ampere. So it is equal to 5.19 watt. So his suggestion is correct. You have to mention that thing how they are mentioning it. One, the P is, if you make it in two significant figures, it is equal to 5.2 watt, right, which is less than half of 13 watt. So the solution is correct. Okay. So in this case, you will get marks for this one, right? 1 mark, and to take the answer 1 mark over here, and here to find the voltage, you'll get 1 mark, right? And use uh, the voltage divider with and current 1 mark, and for the final conclusion with the this one we get 1 mark, right? uh,